Welcome back to our series on the FFT. If you're just joining us, we've covered a lot of ground in the previous parts of this series. We started with PFFT patchers, and then using the FFT tilde and IFFT tilde objects, and even the JIT FFT object in subsequent parts. So while discussing the choice of FFT size, the role of windowing, the number of overlapped FFTs to use, and then we also we've created several different audio effects and we've visualized the results of those. In the fourth installment, we had a lot of fun creating a Max for Live device that used independent delay lines and feedback, and we could do any sort of processing we wanted to do there with each band of audio in the FFT. And then last week we really went crazy and we created some Max externals in C. This week we're going to come back into Max patching land, and we're going to try and understand a little bit more about the mathematics behind all of this magic in the FFT, and then use that to get a little bit of an understanding of phase and how phase is represented in the FFT. Before we do any of that, we can quickly switch over to the website, and in our last series, even if you didn't watch the last series because you weren't interested in the programming, you still can download the package that we created. So I'm going to download this package so that we can use the externals to do some patching today. So I'm going to go ahead, we'll find this. This is the FFT Part 5 package, and you'll see in here there's externals that we built for Windows 32-bit, Windows 64-bit, and then Macintosh. So that's all in there, regardless of the platform you're using. We can drag this into your Documents Max 7 Packages folder to install the FFT Part 5 package. And now we should be able to switch back over to Max, and we'll be able to use that package. If we want to just test it real quick, you can pop open this help patcher, turn on the audio, and see that, oh, we need a sine wave. And we can see that it's working, so that's great. So back in our Max patch now, when we review the objects we've used to perform an FFT, we can remember that we are taking input in the time domain and converting it to the frequency domain. In our case, the input is a collection of audio samples, and each one of those represents the next moment in time. The output then is in the frequency domain, which means that each consecutive output is not the next moment in time, but rather is a number representing the next bin or band of frequencies. So we're emulating that in this patcher right here using a JIT matrix. We've filled up this JIT matrix with a vector which is going to contain a sine wave. We set the frequency of the sine wave here. How we do that is contained in this patcher, and we showed how to do that in part 3 of this series. So this matrix now has a sine wave in it, and we can see that the sine wave, if we take the information about the sine wave, it has one plane, and if we follow the patch cord all the way down, we can see the contents of this. And the contents of it are a sine wave that are going up and down like so. And there's a visualization of it here as well. So that's the input to our FFT. In this case, we're using JIT FFT, but it's a similar situation with FFT tilde or the PFFT tilde objects. We have a real input, which is to say we have real numbers coming in. And what's coming out is a complex number. So that means we have a complex number coming out for each bin. But what is a complex number? Most of the time in Max, and most of the time in our day-to-day life, the numbers we encounter are real numbers. And a real number is exactly what it sounds like. It's a real number. It acts the way you expect a number to act. And it could be almost anything, like a fraction or a whole number or a negative repeating decimal or the constant pi or what have you. You can perform all kinds of math operations on real numbers, and the result is typically also a real number. There is an exception to that, and that's what this little box up here is all about. If we look at the square root, we know that the square root of 4, for example, is 2. And as we change this, it could be any number. Square root of 9 is 3. But what happens when we get the square root of negative 4? Well, nothing can be multiplied by itself to equal negative 4. So the square root object is going to return not a number. But that's not really true, that the square root of negative 4 is not a number. It's just not a real number. And that's because the result is an imaginary number. So an imaginary number might sound a little crazy if you aren't a mathematician, but it is a thing. And in the math world, we represent an imaginary number by writing an I or sometimes a J next to the number. And so the square root of negative 4 would actually be 2i, because 2i squared is going to equal negative 4. So I've created a patcher here, and this patcher is going to calculate the square root, but it's aware of this phenomenon of imaginary numbers. So if we tell it 4, it's going to tell us the square root of 4 is 2. If we tell it 36, it'll tell us the square root of 36 is 6. But if we tell it negative 36, the square root of negative 36 is 6i. It's an imaginary number, as opposed to what Max tells us, which is negative 36 is not a number, meaning not a real number. Okay, so we've reviewed real numbers, and now we've reviewed imaginary numbers. And maybe you're just taking this on faith, but we're here. And now the question is, what is a complex number? So a complex number is simply a combination of a real number with an imaginary number. So if you imagine that you add a real number and an imaginary number, the result is a complex number. Those two components don't mix nicely, and we keep them separate. So if we were going to add, say, negative 0.75 and 2i, we would just express it by writing negative 0.75 plus 2i. And over here in this right column of this Max Patcher, I've included two references so that you can get more information about complex numbers if you want to review them. One is the Wikipedia article. You can see a plus bi here. A is the real. Bi is going to be the imaginary part. And the whole Wikipedia article is in here. Also, if you're more of a video type learner, here is a review of complex numbers from Khan Academy, and you can watch that as well. And I'll leave those in here in the patcher so that you can come back to them later. So back to the FFT for our input, that's a series of real numbers. But the FFT produces a result that's a complex number, which is why the output of the FFT tilde object, we'll just create one right here, is labeled as real output and imaginary output. Those two things put together are the complex number. In the case of JIT.FFT, it's still outputting just one matrix, but we'll see that the matrix has two planes. Those two planes, as you might guess, one plane for the real, and that is shown down here, and one plane for the imaginary component, which is shown right here. I'll go ahead and click those so that they're showing the accurate thing. Another way to think about this is that the input to an FFT, or the input to a real FFT, uses one-dimensional numbers, but then the output that's produced by it is represented by two-dimensional numbers, where real is a dimension and imaginary is a dimension. We can easily visualize a one-dimensional real number using a slider or a VU meter or a dial or any such UI widget. A two-dimensional number which is what these complex numbers are typically visualized on a two-dimensional graph. To show that, I've created a little JSUI here. And if we open it, the source code is in here. We won't belabor the points of the JSUI authoring today, but we can just use what I've already created. And this little JSUI that I've cobbled together mimics a piece of graph paper. So we have the little squares on it. And 0, 0 is the coordinate that's in the center. We can then graph the number by using the two values as coordinates to be plotted. And to graph a complex number, what we typically do is we use the x-axis, which is right here, to represent the real part, and the y-axis, which is right here, to represent the imaginary part. So you can see I've added the little labels here just using comment objects in Max. So if we want to graph a few points, we can take this output here, which we stashed. We just follow the patcher. We generated our sine wave, ran it through this jit.fft, and then we forced it all the way down here, and we stashed the results in this jit.matrix with the name FFT output. This chopping off the mirror bit in the middle is, again, something we talked about in part 3 of this series. So we know that we have the output here in this particular matrix. So then we have this little patcher here, which is going to go through and it can fetch a cell out of our matrix, which is our FFT results. So if we fetch cell 6, then here's cell 6, and it has two parts, the real part, 0.63, and the imaginary part, negative 0.06. And then those get graphed down here on this point, and it's labeled here. And the way that we write this imaginary number, it's 0.63 plus 0.07i. If we choose a different bin of our FFT or a different band, we can see that the point's in a different spot. And we can see any variety of these spots here as we go through. If we change the frequency of the sine wave that we've generated, say we make it 2 cycles that are in there, then we're going to see different results here. In almost all of the videos in this series, we've taken our FFT, we've fed the real and the imaginary components into this magic cardipole object, and somehow the magnitude came out of this first outlet. So that's being used in this patcher so that we can plot the magnitude response here. We also said that the phase comes out of this right outlet. So what's coming into this cardipole object in the case of the second cell is going to be 0.57 and 0.39. Out of that, it calculates a magnitude, which here is some number. If we look at a different bin, it will be a different set of numbers. The magnitude in the cardipole object happens to be the length of this diagonal line right here. This line right here, which makes a triangle, would be called the hypotenuse. You can see that that's also graphed over here in the Wikipedia article. So the magnitude is the length of this line. The phase is the angle of this from the origin. So let's take a look at another example. Here I have the same sine wave generator, so I can go ahead and chart my sine waves. And here we have the visualization of that sine wave input. We run it through the jit.fft. Out comes a bunch of complex numbers. We've chopped off the mirror image and stashed it in this matrix. Then we can visualize every single bin in the FFT. And what we can visualize is we can visualize the phase with each of these little JSUI widgets I made, and we can visualize the magnitude with each of these sliders that are down at the bottom. So we can see 6 in our case, we've generated 6 sine waves, is coming up strongest. And as I slowly move this around, we can see how the phases are affected, and we can see how the magnitude is affected. And we can see those phases swinging around. If I use just noise to fill this, we can see that everything is random values. So one thing we'll see is as the magnitude decreases on the slider, we'll also see that the magnitude, or the length of the hypotenuse in these little circular graphs, gets shorter, and then it gets longer on the ones as it strengthens. We also see that the phase is changing as the frequency decreases. So now let's adapt this to show us an example that is in the audio domain. Okay, so let's duplicate this, and then we'll convert it into a version that's going to work with audio. I'll open this up where we can get rid of some of this jitter stuff. And we can shift all of this upwards a little bit. And now we can get started. We're going to make an FFT. We're going to use size 32. Everything's already set up for size 32 FFT, so we'll just stick with that for now. We're going to use our FFT normalize object that we made in part 5 of the series. We'll hook up the real and the imaginary parts of that. Then we'll go ahead and use this magic card-to-pole object for the moment at least. And then we'll convert this to a list, FFT list tilde. Okay. Hook up the real and the imaginary, and this object also needs to know the number of the band. For an input, we can come over here and just grab whatever sound we wish to use. You can hook that up like so. This FFT list is going to be outputting 32 real numbers and 32 imaginary numbers because the FFT size is 32. But the input to the FFT is only using the real input. We're not using the imaginary input, and that means that the spectrum will be mirrored, and the last half of the spectrum will basically just be duplicate information. So we only need the first 16 values. So I use a ZL slice object to slice off just the first 16 real numbers and the first 16 imaginary numbers. If I use a multi-slider here, I can then visualize the magnitude response, remember because we have a card-to-pole object here. And that's assuming both that I turn on the DSP. I'll make a little easy DAC object here with local mode turned on so that it only turns on the DSP for this patcher. Okay, now it's playing, and we need to set up a Q Metro be outputting stuff. Okay, so now, okay, so it all seems like zeros. I goofed here. I did not put the FFT size on the FFT list. That is a critical component. So now when I play this back, we can see it's actually doing what it's supposed to be doing. Good deal. We can stop that. And now what we can do is we can take the list, okay, I'm going to get rid of this multi-slider that we're using. We'll even get rid of those. And we'll get the card-to-pole out of here too, so we're just working with the real and the imaginary component. And then we can take this and we can use the unjoin object. Get the 16 values for the real and the 16 values which are the imaginary components, and then we will rejoin them into pairs. So we could do something like that. And we'll give ourselves some more space here. Okay. Give me just a moment to patch this up. Okay, so now we're all patched up here, and when I play this, we can see not only the magnitudes down below, but we can see some phase information dancing around. If I were to change the sound source instead of being this particular sound file and used a noise object, then we can see everything's dancing around more or less randomly, as we'd expect. A couple of things I'd like to point out in this patch. One is we are not using cardipole objects. We're calculating the magnitude here using a formula. And that formula is that we're taking the first number times itself, or squared, plus the second number times itself, which is saying it's squared, and then we're taking the square root of all of that. This particular formula is pretty famous if you don't recognize it already. This is going to be the famous a squared plus b squared equals c squared. That's known as Pythagorean's theorem. And what that says is that to calculate the length of the hypotenuse, which is that long side of the triangle, if we come back over here, it's this long side of this triangle that's formed. You take one of these other two sides and square it, plus the square of the other side, and then you take the square root of that, and it's going to yield the length of this line, which is the magnitude. So, over here, that's what we're doing, and if we play the sound, we'll see as this line gets long, it also sends up a larger magnitude here. To calculate the phase for one of these bins is a little bit trickier, and that's what's happening down here. To demonstrate this, it'll be a little bit easier if we just use a simple sine wave. So I'll go ahead and hook up a cycle object to our FFT. Right now the frequency is 0, so we'll see that bin 0 is showing us maximum magnitude. And if we start cycling, we'll move our way all the way on up until we get to a different bin. Let's just go ahead and pause it there. This number is just showing us what the magnitude is. We can see that well enough with those sliders. These numbers, on the other hand, are actually showing us the phase. So the phase we calculate using the atan2 function. The atan2 function is another trigonometry function, which is, this is a variant of the arctangent function. If it's been a while since you've studied your geometry or your trigonometry, the tangent in this case of these triangles, the tangent would be where you take one of the sides over the other side, and what is that ratio? And so the arctangent is the inverse of that function. But when you're doing those ratios, it doesn't really give you enough information to know what quadrant it's in. For example, the ratio of 0.5 over 0.5 is a ratio of 1. But a ratio of negative 0.5 over negative 0.5, if that was your value, which would be down here, that's going to be also 1. So you don't actually know, like, is the point over here or is it over here? You don't know, is the angle, the phase going to be something over here, or is the phase going to be like all the way over here? So there's a variant of that that's used a lot in computer science, and that's this atan2 function. So it returns us a number, and this number is the angle, or the phase. This number looks funny to us if we're thinking that this is the phase, because if I follow this line up here, it looks like the phase should be over here, and if 0 degrees is this line, then we would expect this to be 90, 180, and then like more than 180, but less than 270. But this is telling us it's negative 2.35. Well, why is that? Well, that's because this is in radians. So we need to convert this from radians to degrees if we wish to work in degrees, which is what most of us think of most of the time. So we divide by pi, multiply by 180, and then depending on what the angle is, we need to flip the sign. And so we can see through here, through this math, that we end up with 225 degrees, which is what we're expecting. So that's the phase of this particular band. So I'm going to go ahead now, delete that, and we can encapsulate all of this into a little patcher that will calculate the phase for us. And then we can get the phase for each of these. We could use the car-to-pole object, but this gets our hands dirty, and we can see inside of the black box to understand the math more ourselves. I'll go ahead and turn this back on. One thing we see is that the audio seems to be pulsing or dancing around or not entirely stable. That's because the frequency is not exactly in the center of one of these bands. So if we take the cycle object, for example, and we just we'll do 1 kilohertz just as something to start. We can see these are yo-yoing around. If we want to know exactly where the frequencies are for each of these bands, remember that we can take the sample rate, which we get from the DSP state object, and then we can divide it by the size of our FFT. So in that case, it's going to be 32. And this is going to be the current sampling rate. So we can see 1378 would be the center of a bin. So if I say 1378, that should be our second bin. And now what we see actually is that the energy is all in this bin, but we see that this is changing slightly. What is the number really for this bin? Oh, 1378.125. So this precision is going to be impacting us. So if I say 1378.125, now we're pegged. We can see that we've come all the way out. This circle represents a magnitude of 1. That's the unit circle. And so we can see that this has a magnitude of 1, and it has a phase of 45 degrees. Okay, so I took a little break because things weren't working quite the way I expected, and I could tell there was a bug. For one thing, I mean, it didn't make any sense that at 0 hertz that the phase was 45 degrees. It should have been 0 degrees. I just kept on going, but then eventually discovered that there was like a bug in this FFT list object. So I have fixed the bug, I've updated the package, and I'm back and this should work the way that we expect it to. So at 0 hertz, as an example, we have a phase of 0. And as I increase this, for example, I can make it 1378. Let me do that. 1378.125, which is what we were trying to do last time. And our phase is 0. We're right in this bin. And now as I slowly move this frequency up, we're going to see the frequency is faster than the frequency represented by this bin. As a result, the phase is moving instead of staying still. If the frequency was lower than the center frequency of this bin, then it would actually move the other way. And indeed, we see that. Eventually, the frequency, if we start moving it upwards toward 2600, eventually that frequency is going to move out of this bin and into the next bin. But in the meantime, the frequency is going to be spinning, or the phase is going to be spinning faster and faster relative to the frequency that's represented by this bin. So as we approach now 26 or 2700, we'll see that it's moved to the next bin. And as we get closer and closer to the center frequency of that bin, it should slow down. What is the center frequency of that bin? $27.56. So go a little bit further. And now we can see it is very close to the center frequency of that bin. So I'm glad we caught that bug. I think that's a good place to leave off for the end of this session. Now that we can see this phase information, and now that we understand this phase information, and how we got there from these complex numbers, we can start doing some additional types of interesting processing with the FFT. For example, if you have a pitch tracker, the pitch tracker, instead of just tracking which bin a frequency might be in, we can actually track what frequency a note is occurring at, because we know what's happening with the phase information. But that is a topic for next time. Until then, happy patching.